A president and treasurer are able to be chosen from a student club consisting of 50 people. How many choices are possible if... We're going to run through a bunch of examples, or a bunch of scenarios here. So let's just start out with the how many choices are just possible, period. I.e., if there are no restrictions. And then we'll start doing some more complicated scenarios. How many choices are possible if there are no restrictions? You're going to choose a president and a treasurer from 50 people. This is assuming, obviously, that one cannot be president and treasurer. So you've got 50 students to pick from. You need to pick 2 of them, and they are distinct roles. So that is 50p2, which is going to end up being 50 times 49. That's 2,450 different choices. All right, now let's spice things up a bit. Let's say Garen will serve only if elected president. Garen is one of the 50 students in the club, and Garen will serve. He's like, I'll do it, but I'm not going to be treasurer. I don't want that work, but I will be president only if elected president. We'll just use capital P for, let's not use capital P. Let's write out president because we use capital P for permutations. So, president, I guess, prez. There we go. So how many choices are possible if Garen will only serve as president? All right. You have 2 distinct, or let's be clear. There are 2 disjoint, or another word for disjoint, remember, mutually exclusive cases. Mutually exclusive, as in there's no overlap. Remember, there's no overlap if things are mutually exclusive or disjoint. Garen is either president or not. And any scenario, any event where Garen is president does not appear where Garen is not president. These are mutually exclusive cases to consider. So let's say for the first one, Garen is selected as president. If Garen is selected as president, then how many possible cases are there? Well, you have 49 people to choose for treasurer. 49 possible choices for, let's just do treasurer, T-R-E-A-S. We'll shorten that up, treasurer. Okay, so there's one subset. Second exclusive case is Garen is not selected president. Garen is not selected as president. If Garen is not selected as president, then think about what happens. You still need president and you still need a treasurer. So you still need to pick 2 things, but you're no longer picking from 50 people. Garen is out of the mix, so you are picking from 49 people. So that would be 49p2. And that would be 49 times 48. We can run that through a calculator. So there are 2,352 options associated with that. Because these are mutually exclusive cases, we can just add up the sample points and not worry about double counting. Because again, they're all disjoint. So we're not double counting anything. And so we can say then in total here, there's 49 plus 2,352 scenarios. 2,401. 2,401. And as a quick logic check, the number of options that we have in Part B should be less than the number of options for Part A, right? Because in Part A, there are no restrictions. And in Part B, we do have a restriction. Garen will only serve if elected president. So the fact that the 2,401 is smaller than 2,450 is at least just a good, quick logic check to say that seems reasonable. Spice things up further. Let's say that Zaya and Rakan will only serve together or not at all. Then what? Then how many options do we have? Zaya and Rakan will only serve together or not at all. So that means either there's two people and there's two positions. So either president and treasurer are chosen from Zaya and Rakan, or they are not. Period. And those, again, that's two disjoint cases, right? Again, we have two disjoint cases. So we can count the number of sample points in each of these cases and just add them together. So let's do the first one. Let's say that they serve together. They serve together. Then one of them is president and one is treasurer. So how many possibilities do we have? Two. Two possibilities. Either Zaya is president and Rakan is treasurer, or Rakan is president and Zaya is treasurer. Two possibilities. Second disjoint case would be they do not serve at all. Do not serve at all. Well, if neither Zaya nor Rakan is president or treasurer, then you still have to pick two people to be president and treasurer, but you don't have 50 to pick from. You have 48 people to choose from. So this would be 48 P2. 48 times 47 then is 2,256. And so in total, we will add these together, and we don't need to worry about double counting because these are disjoint cases. So in total, we have 2,256 plus 2 is 2,258 if we add these two numbers together. All right. Good. Let's spice it up one more time. Let's spice it up one more time. Let's say that Garen, in this scenario, let's say Garen and someone named Darius, they don't like each other for whatever reason, and they will not serve together. Let's say Garen and Darius will not serve together. In this case, how many possibilities are there? Okay. This is not quite as simple as the other two. Think about all the disjoint cases you can have. They will not serve together. So, one of the potential disjoint cases is Garen serves, but Darius doesn't. But not Darius. Okay, and then we can count that. The flip side would be Darius serves, but not Garen. Okay, different from number one. But that's not it, right? What are the possibilities? You can either have one of them serve, which is in these two cases, and they're different depending on who it is. They will not serve together. So you cannot have Garen and Darius as president and treasurer, but there's nothing that says they can just both not be elected president or treasurer. So there's a third disjoint case where both Garen and Darius do not serve. All right, and that would be our three cases. Let's go ahead and count these out. Number one, Garen serves, but Darius does not. Okay, so Garen can either, if Garen serves, Garen is either president or treasurer, right? So you got two options, right? Garen is either president or treasurer. So there's two choices, essentially, right? Two choices. Now, for each of those, you need to choose the other position, right? For each of those, how many remaining people are there left to fill that spot? There are. So you started with 50. Garen is one of them. And Darius is out of the mix. So there are 48. 48 choices for the remaining position. The remaining position. And so for each of those, so 2 times 48, 2, this is a two-stage multiplication rule, 96. You have 96 ways. Second case, Darius serves, but not Garen. Looks like I forgot the N on Garen. Oops. This is symmetric to the first case. It's just Darius versus Garen. It's going to be the exact same counting process, except you're excluding Garen. So the number of ways it can be done will be the same. 96 ways, right? 3. Both Garen and Darius do not serve. So you started with 50 people. Garen's out. Darius is out. There's 48 left. And you need to choose 2 people as your president or treasurer. And so 48P2, 2,256. We have 3 distinct things here. And so we can just add these together to get our total. Total will be 96 plus 96 plus 2,256. And that would be 2,448. Bingo. There we go. All right. So these questions can get a little bit more complicated, especially when you have multiple cases to consider. I'll mention something like this last part, part D, where you have something like Garen and Darius will not serve together. And you have 3 disjoint cases. The more disjoint cases you have to consider, the more tedious, the more complicated it gets, and potentially you have more room to make mistakes. What you could do is you could look at the opposite scenario, and I'm going to offer up an alternative solution that's a little bit more clever and more efficient, if you will. And this is using, according to the terminology we had before, this is using the complement of the desired event. Using the complement. The complement of the scenario in part D. What is the complement of Garen and Darius not serving together? The opposite of that, the complement, is that they do serve together. Both Garen and Darius serve together. Let's count the complement. How many ways can this be done? Well, if both Garen and Darius will serve together, one is president, one is treasurer. There are only 2 ways to do that. There are 2 ways to do this. Okay? Now, 2 is not the correct answer. That's not what we want. But remember, we've counted the complement. And the complement contains all of the events in the event that you don't want to happen, that you should not be counting. So we've counted the opposite. So how can we use this? Well, we know from the beginning that in total there are 2,450 possible ways to do this. Your total sample space has 2,450 elements. 2 of them are in the complement. 2 of them are in the complement, which means we don't want those, so we just take those away. And so there are 2,448 in the event we wanted to originally count. Very slick. Very slick. using the complement. If, and there's nothing wrong with doing this in either way, but the strategy of counting the complement or counting the opposite is very useful, and sometimes it's a lot faster, provided you have a grasp on the total sample space, right? You can't do this unless you know the total sample space. And that will do it for that example. If you do have any questions or are looking for clarifications on these parts, please go ahead and post those in the discussion thread below. All right. Good. I like that. That looks good. All right. And let's do one more. Let's change up the example here. One other type of question. So the key thing that was in this last problem was that we were using permutations and we were looking at potentially disjoint cases and how to count those. Here's another type of question. It's got a very specific style to it that requires a different strategy. And you've quite possibly seen something like this before. How many different strings can be made from the letters in the word Mississippi? How many different strings can be made from the letters in the word Mississippi? M-I-S-S-I-S-S-I-P-P-I, I believe is the correct spelling. M-I-S-S-I-S-S-I-P. Yep, that looks good. Using all the letters. Using all the letters. And when we say how many different strings, what we mean there is just a string of letters that does not need to be an actual word in the dictionary. So just how many ways can we sort of arrange the letters of the word Mississippi, making sure that we use all of the letters. All right. So here's how I'm going to ask us to think of this. What do we have here? We have, how many letters do we have in total? So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 11 total letters, all right? There are 11 total letters, all right? So let's take an easier problem. If you could tell the difference between all these letters, let's say they weren't repeated, because where this gets complicated is you have multiple S's, multiple I's, and that kind of stuff. But for example, if it was just the first 11 letters in the alphabet, A, B, C, D, E, F, G, H, I, J, K, L, whatever, right? That would just be 11 factorial. That would just be a straight permutation, just be 11 factorial. The problem is, in order for these strings to be different, we have to be able to tell the difference between the letters. But look at the example in this word right here, Mississippi. We cannot tell the difference between this S and this S and this S and this S. There's no difference. If I'm going to go ahead, let's say I label these behind the scenes as this is the first one, this is S2, this is S3, and this is S4. But if I have Mississippi, M-I-S-S-I-S-S-I-P-P-I, and I say, well, this is actually number 2, this is number 1, this is number 3, and this is number 4. These are not different strings. These are the same. These are the same. But there's more ways for this to happen, right? Because I can reorder my S's and you can't tell the difference, right? You can't tell the difference. If these are not labeled, you cannot tell the difference, and they are not labeled. They are just, we have 4 S's. So how do we account for the fact that these S's can be arranged in here? Well, you need to divide that out. So what are you going to divide out? Well, how many ways can I get this exact string, M-I-S-S-I-S-S-I-P-P-I? Well, look at the letters you have repeated. These S's could be done in any order, right? What if you had the 4th S, the 3rd S, the 2nd S, and the 1st S? How many ways can I arrange these 4 S's? If you could tell the difference, that would be 4 factorial ways, if you could tell the difference. So we need to divide out those 4 factorial, because that's going to show up this one can show up that specific string and this specific ordering can show up 4 factorial ways without noticing the difference because these S's are repeated and you can't tell. But we have other things that repeat, right? What do we have that repeats here? We have so the number of S's that we have, the number of S's, there are 4 of them. The number of S's. There are, how many I's do you have? You have 1, 2, 3, 4 I's. And then how many P's do we have that repeat? There are 2 P's. So for each of these, we're going to have that same thought process. I need to divide out the possible reorderings of I's that you cannot tell the difference. That's another 4 factorial down here. And I need to divide out the P's that could repeat as well. That's another 2 factorial. That's another 2 factorial. Okay, another 2 factorial. And in fact, if you want to be complete, you could look at the number of M's. You can actually do this in general. The number of M's, there's only 1 M. And so you could say that's going to divide out 1 factorial. But 1 factorial is just 1, so you're not actually changing anything. But what this does is it sort of helps give you a complete process. Just count the number of letters you have, and you want to divide out the number of times that that letter could be repeated in a different order where we can't tell the difference. So it's 11 factorial divided by 4 factorial, divided by 4 factorial, divided by 2 factorial. And we need to work out the arithmetic and multiplication on that. Check your skills with your factorials here. You should be able to get 34,650. And if not, something's going wrong, and maybe ask for help on that in the discussion thread or schedule an office hour to talk about how you're keying things in to make sure we can get that number. Okay. So this is a very common type of question. How many different strings can you make when you have an ordering of letters that are repeated here, that are repeated, right? And this is formalized in our e-text in Theorem 2.4. The number of distinct permutations, of n things, of which n1 are of one kind, and 2 of them are of a second kind. So on and so forth, yada, yada, yada. Maybe we have k different types. There are n sub k of the kth kind. The number of distinct permutations is n factorial divided by n1 factorial, n2 factorial, n3 factorial, yada, 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 n sub k factorial. Okay. And really, this theorem is just formalizing the logic that we developed to answer this question here. Okay. Theorem 2.4. You're just dividing out the number of repeats that you'd have there. Notice that in the general permutation, the original permutation where you have a set of n distinct objects, if they're all different, like if I have the letters A, B, C, D, and E, 1, 2, 3, 4, 5 of them, right? And these are all different. How many ways can I arrange these letters? You'd have 5 factorial. You have 1A, you have 1B, 1C, 1D, and 1E. And 1 factorials are all just 1, so it's just 5 factorial, right? But if you throw in a repeat letter like an A, then all of a sudden that changes, and you're going to have 5 factorial over, we'd have 6 factorial, because we have 6 letters, and the A repeated. And then you have the rest of your 1 factorial, 1 factorial, 1 factorial, yada, yada, yada. So that would just be 6 factorial over 2 factorial. Okay. All right. We're going to go ahead and pause here. We've got one last thing we want to look at as we're starting to get to permutations of things where we have repetitive objects. We're going to continue down that path a little bit, and we'll see you in the next video.